Okay, so we're recording here. Example 4 deals with work needed to empty a tank. Okay, so in this problem, you have a tank that has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It's filled with water to a height of 8 meters, and we want to find the work required to empty the tank by pumping all the water to the top of the tank. And incidentally, the density of water is 1,000 kilograms per cubic meter. Okay, and if you were dealing in foot, like feet and pounds, the density of water is 62.5 pounds per cubic foot. Okay, so, but right now we're dealing in metric units, so the density of water is 1,000 kilograms per cubic meters. So just like with the, with the problem where we had the, pulling the cable to the top. Pull it, like moving the elevator up 30 feet. The top 30 feet of cable, in that last example, we divided that up into pieces of cable and effectively found the work required to be to bring up each piece of cable to the top of the building, and then added all those pieces of work together, added them up, Riemann sum, took the limit, got an integral. It's the same kind of situation here. Let me show you the tank. Okay, here is the tank in figure 3. Okay, so the tank is 10 meters tall. It's an inverted tank. Okay, 10 meters tall, 4 meters the radius, and the water is filled 2 meters. Well, it's filled, the bottom 8 meters of the tank are filled. 2 meters of air on the top of the tank. So just like with the cable problem, where we took the cable and broke it up into little pieces of cable, we're going to take the water and break the water up into slices of water. Okay, discs of water. Okay, and every disc of water has a radius, r sub I, and it has a width, delta x. So all the slices of water have the same width. Okay, but the radius varies, right? Depending, the radius for the ith layer of water, that's that purple layer there that you see in figure 3. The radius of the ith layer of water varies depending on how far down that ith layer of water is from the top of the tank, and that distance is x sub I. Okay, so of course in this problem we need to find out, the integral is going to be an integral with respect to x. So the radius of the ith layer of water, that ith cylinder of water, we need to find what that radius is in terms of x sub I. So we can use the fact that how many recall similar triangles from their geometry days? Similar triangles. Okay, Maria recalls that. Jacob recalls that. What they do is they take this tank, okay, and you have two triangles. You have two triangles. If you look at the tank, there are two similar triangles. So one triangle is 10 meters high and 4 meters across. That's the big triangle that goes from the bottom of the tank to the top of the tank. Okay, but then you have another triangle that goes from the bottom of the tank to the ith layer of water with radius I. Now that ith layer of water is xi meters from the top of the tank. So from the bottom of the tank, that ith layer of water is 10 minus xi at 10 minus xi meters. So based on similar triangles, if we take the radius, the r sub I, and divide it by 10 minus xi, that's going to be equal to 4 over 10 by similar triangles. And so the radius here, the r sub I over 10 minus xi, okay, the ratio of the radii of the triangles is equal to the ratio, no, I'm sorry, the radius of the, I mean, think about the smaller triangle. The radius r sub I over 10 minus xi is equal to the radius of the big triangle, 4, divided by the height, 10. And so r sub I will equal then 2/5 times 10 minus xi. 4/10 reduces to 2/5. Multiply both sides of the equation by 10 minus xi. The radius I is equal to 2/5 times 10 minus xi. All right. Are there any questions on that before we move on?
Can you scroll back down?
Yes. Scroll down here.
Yeah.
Yes. Yes, Marcus.
Yep. Thank you.
Okay. Okay. Well, now what we have to do when we're trying to find the work needed in emptying the tank by pumping out all the water, we need to ultimately get force times distance, because work is force times distance. But what we have to do first is find the volume of the ith layer of water. Now they're saying the volume of the ith layer of water is pi r squared times delta x. Pi r squared times delta x, what's that remind you of? That's the volume of a what? Delta x is the, so look at the height, look at the ith layer of water. The ith layer of water is a disk or a cylinder. The volume of it, that's right, Sean, good. The volume of a cylinder is pi r squared times the height. Well, the height is delta x. And so in this problem, the volume is pi r squared times delta x, but r squared, r is 2/5 times the quantity 10 minus xi. If you square that, you're going to get 4/25 times 10 minus xi squared. And that's how you get the volume. From the volume, we have to go to mass. Okay, mass, how many recall that density is mass over volume? How many recall that? Density is mass over volume. Okay, Sean recalls that, and it's something you should have seen when you were younger. So that means mass is density times volume. Well, the density of water is 1,000 kilograms per cubic meter. Okay, so we take the 1,000 and we multiply by the volume. And when we, 10 minus xi quantity squared, we got a, well, when you work that out, 1,000 divided by 25 is 40, and 40 times 4 is 160. So the mass is 160 times pi times 10 minus xi, that quantity squared, times delta x. Now, from mass, we get to force, because force is mass times acceleration due to gravity. Okay, so eventually, work is force times distance, so we got to get to force. Well, here's the force now. Force, for the force needed to bring up the ith layer, I want to be careful here. The force on the force for the ith layer of water, okay, is equal to mass times acceleration. Well, mass is 9.8 meters per second squared. So you multiply 9.8 times that's the gravity times the mass, and you get 1568 pi times 10 minus xi squared times delta x. Now you have the force, okay, and now you have to worry about distance. Well, in the problem here, you have here the ith layer of water needs to be brought up a distance of xi meters. Okay, so your work's done when you bring the ith layer of water up to the top of the tank. Your work's done for that ith layer of water. So we're basically figuring out the work needed to. We're taking that volume of water, breaking it up into a bunch of layers, and computing the work needed to bring each layer of water to the top of the tank. So in that sense, and we're almost done here, almost done. Okay, the work equals the force times the distance. Well, the distance is x sub I. So now you have the work needed, the work to bring up the ith layer of water, well, to the top of the tank. And all you have to do now is add up all those pieces of work. And when you do that, the Riemann sum is going to become an integral. Okay, and so this is the final step here. The work is the limit as n goes to infinity of that Riemann sum, and that becomes the integral. The limits are 2 to 10 because the water, the layer of water at the very bottom of the tank needs to be brought up 10 meters, and the layer of water near the top of where the water is. Let me just show this real quick. The water here. Okay, the water, the top layer of water is 2 feet from the top of the tank, so that only needs to be brought up 2 feet. So therefore, the limits go from 2 to 10. And when you work that out, you're going to get 3.4 times 10 to the 6th power joules. And that's an example of finding the work needed to pump water, pump a volume of water to the top of a tank. Okay, how many think that's absolutely fascinating? Maybe give me a few thumbs up if you, and it's going to take time to learn, but Jacob's liking it, and Sophie's liking it, Nathan, that's excellent, excellent. Michelle, wonderful. Are there any questions? Any questions at all? Jacob? Yep. Jacob's good? Okay. Jacob likes it too.
Sorry, I just forgot to put my hand down.
Oh, no problem, Marcus. So, all right. So, you're finding this interesting. I like that. Let me stop the recording here.